So, you guys should have some background. Excuse me, some background in chapter 14. I did pass out your chapter 14 note packets there. Let's kind of go through and talk about some of those. The point of this chapter is the basics of probability, right? The overall, like the underlying concepts of probability. We're going to go pretty deep in the next 4 chapters, but really these first 2 kind of establish how we calculate probabilities, some of which is going to be reviewed for you. For example, some of these vocabulary words here should be, well, at least trial and outcome and event you should have seen before. But we're going to go in and talk about the fundamentals of probability, the background information, and then we will do some actual problems, some real math problems, which, we haven't done a real math problem all year, so we should probably do a couple. So a couple of vocabulary things to keep in mind. So first of all, is this thing called a random phenomenon. A random phenomenon is a situation in which we know what outcomes could happen, but we don't know which particular outcome did or will happen. Flipping a coin is an example of a random phenomenon because what are the 2 things that can happen? Richard, what are the 2 things that can happen when I flip a coin? What if it lands like right on its side? Oh, okay. It has happened, right? But I mean, it's a very, very low probability that it's going to happen, but it has happened. It can bounce and then it can start to spin, and then the spin just starts spinning, right? It was like one of the greatest moments of my life when that actually happened. So, we know what can happen. It can be heads, it can be tails. That's the most likely things. But we don't know what will happen anytime. In fact, with a flipping the coin, there's an equal probability that it could be heads or tails. And thus, we have a 50% chance of guessing right. We don't know what will happen until it happens. We can just give you a rough guesstimate of the likelihood that something will happen. Okay, and that's a random phenomenon. There's lots of things that are random phenomenon. The most basics from playing games, drawing cards, rolling dice. Those things are random phenomenon. But there's also random phenomenon that you can see in life. Psychology is kind of the study of human beings and how we can be somewhat random as well, right? We don't necessarily every single time. What am I trying to say? In the study of psychology, sometimes you can have some kind of background on some person, like abuse or something like that. And some individuals will react to it this way, and some individuals will react to it this way. And so there is some random phenomenon there as well. It's got bias and everything introduced, but it's still random, right? So random phenomenon, basically the study of these events that we don't know the outcomes of. In general, each occasion upon which we observe a random phenomenon is called a trial. Every time I flip a coin, that's a trial. Every time I flip a coin, every time I roll a die. Each trial, we note the value of the random phenomenon and we call that an outcome, right? Heads, that was my outcome, right? Tails, that was my outcome. When we combine outcomes, the resulting combination is an event. I got 4 heads and 1 tails. That was an event. I've got combined outcomes of that. Okay? And the collection of all possible outcomes is called the sample space. So everything that we can possibly come up with is the sample space. For example, the sample space for flipping a coin is heads, tails, and then on its side, right? Because technically it can happen. So that would be my sample space. And we would have a probability associated with those, which generally would be like less than, how would I write that? Less than like something like that. On its side is a very small chance of that. The sample space is the combination of everything that can happen for a given event. Now, one of the things to think about on the sample space is it's determined by what the question says. For example, if my question was, what's the probability of getting heads 2 times in a row? That changes my sample space. What are the possibilities of flipping 2 coins? Devin? Well, instead of actually, don't give me you're correct, right? But I want to say, what's the sample space of getting 2 heads? In which case, I need to write down all the possible outcomes. So what's one possible outcome of flipping 2 coins in a row? Heads, heads. What's another possible outcome, Bryce? Tails, tails. What's another possible outcome, Courtney? Tails, heads. And what's another possible outcome, Jared? Heads, tails. Okay. So on its side, yeah, I guess, and yeah, we could add an on its side to all of those things, right? But because that one's less than 0.0001, we're just gonna assume that we're gonna take that one out of the equation. But you are correct. So we've got 4 different outcomes, and notice all we did to change the sample space there was change the framing of the question. I framed the question as has the probability of getting 2 heads in a row. Suddenly I'm flipping 2 coins. That changes my sample space. It changes the outcomes that could happen. Okay. So vocabulary, right? Ways that we're going to be framing our arguments here in this chapter. I think this is where your notes actually start. The beginning of the law of large numbers stuff. Go ahead. 0.016. Wow, that's a lot higher than I thought. Okay. 1 in 6,000. So that needs to alter so that it's a 0.016. So I assume then that we need to change these to reflect that. 0.484. Am I right there? No, I want to split that in half. 0.492. There you go. Right, if you want an appropriate sample space for that. Okay, anyway. So, first definition of law of large numbers, we're going to do it fairly quickly because we talked about it with the tax. One thing about what happens with the combination of outcomes, things are simplified if the individual trials are independent. Can somebody raise your hand and tell me what does independent mean again? This is the concept we talked about, Justin. One does not affect the other. When we were dropping tax, were the tax drops independent? Yes? No? Give me a shake of your head. What do you think? Yes, yes. The tack drops were more than likely independent. Dropping a tack on the desk, the one is probably not going to affect the other. The tack is not causing such an indent on the table that it's going to change that it's going to inadvertently cause something to go one direction all the time. So it's probably safe to say that it's independent. So we want to make it easier to talk about the law of large numbers when things are independent. Roughly speaking, this means that the outcome of one trial doesn't influence or change the outcome of another. For example, coin flips are independent. The law of large numbers says that the long run relative frequency of repeated independent events gets closer and closer to a single value. And from what it looked like on our tack dropping, is that tax side up was probably going to get fairly close to 60%-ish, right? Maybe it was getting to 59.8%. We don't really know that. Maybe it was getting to 58.6% and we were a little bit high, and that the other values were going to take it lower. We don't really know that unless we would drop a lot more tax, okay? Which we could do, but the value of that time could probably be better spent elsewhere, okay? But as long as these events are independent of each other, the long run frequency should get closer to a single value. And that single value is called the probability of that event, okay? That long run value that the long term frequency is getting close to is the probability that something will happen, okay? And because this definition is based on repeated observing the event's outcome, we often call this empirical probability. Empirical probability basically just meaning that it was observed. Sometimes we call this, or you might have heard of this as experimental probability. The reason why we're coming up with a probability is because we've experimented on it, and that's what we've seen. That's what we've observed. Empirical often means observed, okay, or something along those lines. Any questions, comments, concerns here? Okay, let's talk about the law of averages. And I should say the non-existent law of averages. The law of averages is something we want to believe, but it's absolutely not true. So the law of large numbers says nothing about short-run behavior. The best we can say in a situation concerning a series of outcomes, we need lots and lots of numbers to be able to come up with something. Doesn't say anything about short run. Relative frequencies even out only in the long run, and this is the really, really long run, okay? Even the 500 something that we did is not long enough to really see a long-term frequency. You need thousands and thousands and thousands to really narrow it down. In fact, to be technical, you want infinitely long for that. The law of averages says that an outcome of a random event that hasn't occurred in many trials is due to occur, doesn't exist. But we are tempted to believe it exists, right? And let me give you an example of that. Somebody have a quarter? Where's one? Quarter is easier because it's easier to split. So I flip a coin. Heads. Is my next coin flip more or less likely to be a head? Equally the same. Okay, so I flip the coin again. Heads. Wow. Is the next time I flip a coin equally likely, less likely, or more likely to be heads? Flip the coin. Heads. Wow. So I've gotten 3 heads in a row. Any of you guys getting nervous? No. Connor? We still want to talk about it in terms of independence. Yeah. Okay, that was 3 heads in a row. I flip a coin. It's heads. Wow. If I were to ask you all what the next one's going to be, using your evidence right here for this 5th coin flip, are you going to choose heads, tails, or heads or tails? I guess it's going to go off the side. I'm grabbing it like this and slapping it down, so we know that side isn't going to happen. Now, if I were letting it hit the floor, then that's a possibility. Do you think it's more likely to be tails next time? Nope, still heads. It's 5 in a row heads. Anybody getting nervous? You want to choose tails next time? I mean, it's been 5 heads in a row, so this one has to be a tails, right? But that's not how randomness works. This is the law of averages. The fact that 5 heads have occurred does not change the fact that it's still a 50% chance of being heads, right? Every time I flip the coin, heads, 6 in a row. Every time I flip the coin, it's equally likely to be heads every time. The fact that there were 6 heads in a row beforehand doesn't change that. This is still a 50% chance of being heads. Heads again, that's 7 in a row. Anybody feeling nervous and want to choose tails, thinking that it might be tails this time because we've gotten so many heads? It's still a 50% chance, right? Heads. 8. Heads. 9. Heads. 10. Anybody want to choose tails still? I mean, are we getting nervous that there's been 10 heads in a row, so now tails has to happen? 11 heads in a row. The head. 12 in a row. Okay. There's been 12 heads in a row. Is anybody nervous and you want to choose tails? Now here's the thing about law of averages. How many of you guys are thinking online just because there's been 12 heads in a row? But every time I do it, it's still a 50% chance of being ow. The fact that there's been 12 heads in a row has no influence on the next one. This is the problem with the law of averages. We want to believe it because we think that just because something has happened so many times in a row and it's only got a 50% chance of happening, we think that it's not going to happen again. Right? This is the issue with law of averages because it's really tempting to believe. It's really tempting to believe that just because something has happened so many times that we're more likely to see it not happen. Whether or not I'm telling the truth or I'm lying, some of you guys think I'm lying just because it hasn't happened. And that's a problem. I'm never going to tell you guys if I'm telling the truth. Just get used to that. Okay? There's a lot of times in class where I'm going to not tell you.
I feel like this is putting a strain on our relationship.
So, that's the thing. Whether or not this is another tails or a heads, a lot of you guys believe I'm lying because so many heads has happened in a row. But you shouldn't, because this is the law of averages. The fact that 12 heads happens in a row doesn't mean that the 13th one has less of a chance of being heads. Okay? Think about sports references. How many times have you heard of people having like the hot hand, like they're on fire? They get 10 shots in a row, suddenly they can't miss a shot. Right? Pass it to that guy because he can't miss right now. Just so you guys know, there's no statistical evidence of that ever happening. Okay? You're seeing short run behavior. Yes, a person might make 12 shots in a row, but honestly, in the long run, they make 80% of their shots. You're just happening to see a string of 12 in a row that they're hitting. But you know what? You follow them a little bit later, they're going to start missing those shots, and they're going to keep that 80% average. Okay? So, long run behavior, it's getting closer to where their actual batting average should be, the actual probability that they're going to hit something in. That's short run behavior, right? Maybe the batting average that led them up to be that high is the part that's not correct, right? Because they had a string of good games in a row, and long run behavior is gonna even out to where their batting average should be, the actual probability that they get a hit.
So along with like sports and all that, like
psychology does play some toll in that, right? Maybe, it could. It could. Shaking confidence, yes, could have an effect. I will agree with that. Mm-hmm. Why were you being rude like that?
I'm better at myself
because you didn't know that?
Yeah. Well, no, I'm better at myself because I was at the play all night, so I didn't do my notes.
Oh, okay. Yeah, and we could also even probably lump that under, what's that thing we were talking about? Placebos? Is placebo what I'm saying? Yeah. We may even be able to lump that under being something like a placebo, where you think it's having an effect, but it's really not. Brittany, go ahead and say your thing.
I have a question about placebos because if you're going to like big numbers, because
I'm going to make fun of you anyway.
Yeah, anyway, so I was watching Grey's Anatomy and then they did this clinical trial where they like.
Do you think I'm going to make fun of you because you watch Grey's Anatomy?
No, because I really.
Because that's really what I'm going to make fun of you.
Yeah,
okay.
So they like have these envelopes that have like a drug or placebo on it, so it's just like daily, and then like they don't open it until they're like in the surgery, and then like she switched it, but like would it? Yeah, bam. So why if like so like they would the doctors would have known if it was a placebo or not when she switched it, but it wasn't affected the trial, so why was it that?
So they were doing like a drug trial in a surgery.
Yeah.
And they were unmarked envelopes.
Yeah, but then she went and she like held it up to the light and she was a placebo and she wanted to placebo and she switched them. And then so she didn't use she wanted to get the drug, but was that actually like
Oh, so the reason why that's bad is it would taint what's happening. It would be introducing bias into the trial because you now have a person who's involved in the trial knowing which is which. Would be my guess. So is the doctor administering it? I don't know. I guess it would still be double blind. I don't think I understand why that would be bad. Aside from that, maybe it was just dishonest of the nurse. Yeah, I can't see a reason why that would actually taint the experiment at all. I think the writers were probably like, this is an interesting way to introduce drama. Yeah, I mean, if the doctor administering it still didn't know, it's still double blinded.
No, the doctor didn't know either way. They were like, everybody's got one.
Yeah. Anyway. That's true. We do lose some randomness in the experiment. That's true. Because maybe she, being assigned to a certain group, that could be introduced to bias. So yeah, okay. Okay, anyway, law of averages question. It is a very tempting thing to believe, but it's not true. Short run behavior doesn't affect. Huh? Is it true with dependent variables? Yes, it is true. If we don't have independence, then it would be, because for every event that, like, if I'm drawing students from the classroom, and we're saying what's the probability of drawing Connor, every time I don't draw Connor, the probability of drawing Connor goes up. So yes, if we lack independence, then law of averages is something that could be true. I was thinking about taking it. If it was Aiden's quarter, I would have taken it. But yeah, no, of course not. You're a drama major. What are you gonna do? That has zero impact. In fact, that's the opposite. You're a drama major. You really need the money.
Need money.
Yeah. So when probability was first studied, a group of French mathematicians looked at games of chance in which all the possible outcomes were equally likely. They developed mathematical models of theoretical probability. In fact, some of these games we're going to play, not this chapter, we're going to play them in 2 chapters when we start talking about this thing called expected value. But we will, in fact, play the game of chance that first started probability as a mathematics. Anna. Why does that make you angry? But the textbook is kind of funny. I like that, Joe. I like it. That's one of the reasons why I like this textbook. Because I think it's hilarious. It's really cheeky. Sorry. Yeah, you got to read the footnotes. You got to read the side notes and all of those things. But see, don't skim. That's the problem. You find it boring because you're not actually reading. So. Yes, this is a short chapter. We're gonna listen. We're gonna do some things in this today, and then we're basically gonna finish it up on Monday. So. Okay, but anyway, so we're gonna play these games of chance. But basically, so you guys know a synopsis of what happened. There was a French gambler. He wasn't even a mathematician. He was a French gambler. He used to go to taverns and he would get people to play this game with him about rolling dice. And people started to catch on that he would win more often than he would lose, and they'd stop playing with him. So he changed the game, and suddenly he started losing more often. And he didn't understand why. So he went to his friend who was a mathematician, and that's how probability as a mathematical science kind of was born. It was because a French gambler was trying to earn more money from people in taverns. Okay. So theoretical probability is where we're not talking about empirical evidence, things that we have seen. We're talking about a model that represents it. So things like it's equally likely to get 1 of 6 outcomes on the roll of a fair die. Okay. It's equally likely to get heads or tails from the toss of a fair coin. However, keep in mind that events are not always equally likely. For example, a skilled basketball player has better than a 50-50 chance of making a shot. A skilled goalie has a better than 50% chance of blocking a goal. Okay, the probabilities are sometimes equally likely. However, there's lots of instances where things are not equally likely, and we'll build probability models to show that. Overall, the probability of an event is the number of outcomes in the event divided by the total number of possible outcomes. I want you guys to pay special note to this notation, right? That right there kind of looks like function notation. You remember f of x from like advanced algebra, Greek calculus, f of x and h of x and those things. This is similar. We pronounce it the same way. That's p of a. And all of that notation means is the probability of event A. So the probability of a certain event is the number of outcomes in A over the total of possible outcomes. When rolling a die, the probability of rolling a 1, right, that's event A, rolling a 1, is the total number of outcomes, 1, divided the total number of possible outcomes, 6. Okay. If we wanted to say we're rolling 2 dice, and we wanted to know the probability of rolling a 7, we need to come up with the total ways that you can roll a 7 divided by the total possible outcomes. Does anybody know the total possible outcomes of rolling 2 dice? No. 2 dice, total possible outcomes? 36. And then the probability of rolling a 7 is the number of ways you can roll a 7. 3 and 4, 4 and 3, 5 and 2, 2 and 5, 6 and 1, 1 and 6. Looks like there's 6 different ways. So 1, 6. By the way, when rolling 2 dice, 7 is the most common number. I don't know if you guys ever did this. Did you guys ever do that probability? It's a really common middle school probability thing where you look at the probability of 2 dice happening. And you guys play the game Settlers of Cont, right? Ty, you're my man right there. Okay. Settlers of Catan, especially if you play the game into online things, they give you an experimental probability of all the dice that are currently being rolled, and the outlook looks like a normal model. 7 being the most commonly rolled thing, 6 and 8 having equal probabilities, 4 and 9 having equal probabilities, 10 and 3 having equal probabilities, no, 11 and 3, 10 and 4, 11 and 3, 12 and 2. Right? What is Settlers of Catan? Oh my goodness, you have things to learn. You don't know what Settlers of Catan is. Catan, C-A-T-A-N. By the way, if anybody's like, I know we don't have a large proportion of gamers in the room, but the reality is that when you go to college, you're going to play more board games because smart people play board games. And Settlers of Catan is a fantastic game that you all should play sometime, right? So, everybody, like, you guys don't think this. Everybody looks at like gamers and D&D people in high school as like being the nerds and everything like that. But the reality is that there are people in this room, they're going to pick up D&D in college, and you're going to be like, oh my god, why didn't I do this in high school? And you're going to be like, well, that's because the people in high school who do it are socially awkward. But they're ahead of the curve because they're just understanding their nerddom now instead of when they're in college. So, Aiden, exactly. Aiden plays lots of D&D, socially awkward.
It's even awkward.
One of the guys, so I meet on a Wednesday, every Wednesday, I have a gaming group that I meet with, like, throughout Bellingham with my friends who play D&D. One of the guys who's in that was like he's a big guy, he was a football player in high school. He was like, if I'd have known my adult self when I was in high school, I would have kicked my own ass because, like, I would have thought that but he went to college and suddenly he became a nerd. Now he's like an investment banker or something like that who plays D&D. who plays D&D twice a week, and yeah. So it can happen to you, Connor McCandless, is what I'm trying to say. Right? You're looking at me like that's not going to be me, but it can happen to you, and it can happen to you, it can happen to you, right? You're all going to be nerds when you go to college, so just get used to it now, embrace it now, okay? Who's Jared Bowman?
He's a football player guy. Really big black guy.
Oh, that guy.
Yeah.
I know that's terrible, but I know that's how I reckon.
The most definable trait of his.
Yeah. Well, but I mean, in Cedar Woolley, that's a pretty definable
Yeah.
trait. Unfortunately, we're not the most diverse community. So when you say the senior that's a big black guy, it really narrows it down to one person. Do we have any more? No. I don't think so. I think we just have one.
You don't even have to say.
No, you do have to say senior because we have some freshmen and some sophomores. But yeah, we're not a we're unfortunately not a very diverse town, so that is a distinguishing marker. So it's sad, but when you go to I went down to when I went to Federal Way, when I went to Todd Beamer High School a couple of weeks ago, it was like, wow, this is not our school. Because you walk into the classroom and you're like, this is not us. Anyway, sorry.
I was from Melbourne, and then I came here. I was like,
all of this being recorded, by the way, so some random person's gonna watch this and be like, what a bunch of racists in Cedar Woolley.
when I moved from Melbourne into here, I was like,
Glad I don't
wow,
live
so
there.
many white people go to the same school.
I had a friend,
Genuinely said,
a buddy of mine from Virginia visited, 5 years ago, and we were just walking around Bellingham, and he goes, don't take this the wrong way. Do you have black people here? Because it was like everywhere, because it's white people everywhere in these towns. Yeah, there is, and it's if you've only lived in Cedar Woolley, and then you go visit these other places, it almost is a culture shock because you're like, I didn't know that this kind of thing existed. I thought the world was 90% white, and then you're like, oh wait,
wow,
it's really not. It's
It's
really not at all. So. Okay, all right. Let's get back to what we're talking about here. So.
This really resets racial stuff.
Yeah. So personal probability in everyday speech. When we express a degree of uncertainty without basing it on long-run frequencies or mathematicals, we are stating subjective or personal probabilities. We kind of already talked about that with Hannah, so I'm not going to spend a lot of time here. They don't display the kind of consistencies that we need, that we'll need probabilities to have, so we'll stick with the formally identified defined probabilities. We'll ignore that. Okay. Getting into some problems now. The first three rules of working with probability, generally speaking, make a picture, make a picture, make a picture. If we can draw out the situation, it becomes much easier to understand. Okay, and probability situations with probability, we have pictures that we can draw for those as well. The main one that we're focusing on right here is called a Venn diagram. How many of you guys have seen Venn diagrams before? Okay, I don't need to talk about it much. Venn diagrams essentially being the circle represents your sample space. And each of the square represents your sample space, all possible things that can happen. The circles represent individual events. Anytime the circles overlap, that's the probability that both of those events will happen. Okay? So, some rules about probability. There's two requirements for a probability. First, a probability is a number between 0 and 1. There's no such thing as a negative number. And there's nothing bigger than 1. Okay? A probability is a decimal fraction between 0 and 1. You can't have more than 100% chance of something happening. You can't have less than a 0% chance of something happening. In mathematical terms, what that means is 0 is less than or equal to P of A, which is less than or equal to 1. The probability of event A happening is between 0 and 1. Number 2, the probability assignment rule, which states that the probability of the set of all possible outcomes of a trial must be 1. If I were to go through like this and make a list of my sample space, like this, these numbers have to add up to 1. If they add up to something bigger than 1, you have a problem. Because the probability, the sum of everything that can happen has to add up to 100%. If it adds to less than that, then you're missing something. If it adds to more than that, then you've got your probability outcomes wrong. Okay? That means that the probability of S, where S represents the set of all possible outcomes, meaning heads, tails, on its side, has to equal 1, has to equal 100%. So that's a picture of that, right? That's probability of 1, my sample space, S. Complement rule. The set of outcomes that are not in the event A is called the complement of A, and we denote that as A C, or we would actually just say complement A, or A complement, okay? The probability of an event occurring is 1 minus the probability that it doesn't occur. So if I'm looking to find out if I know that the probability of drawing if I'm reaching into a bag of M&Ms, right? And I'm trying to figure out what's the probability of drawing a blue. I can find the probability of drawing every other number, and then subtract that from 1, and that would tell me the probability of drawing a blue. A complement would be the probability of not drawing a blue, and if I know that, I can subtract it from 1 to give you the probability of drawing a blue. True in that particular case, yes. There are instances, however, where the complement rule makes sense given certain information that you have. Okay. So yeah, and then again, in mathematical terms, the probability of event A is 1 minus the probability of A not having A complement. And I think there's a picture of that. Yes. So that's A. That's AC. Everything that's not inside the circle is complement A. To find either of these numbers, I can take 1 minus the other. The addition rule. For events that have no outcomes in common, and thus cannot occur together, are called disjoint or mutually exclusive events. There's a couple more vocabulary words for you. If two events are disjoint, it means they cannot both happen at the same time. And there's a picture of that, two disjoint events. Notice that the two circles are not overlapping in any way. So if one thing is happening, we know that the other thing can't happen. So, for example, the probability of drawing a junior in this class, right? I can't draw a junior randomly and have them be both a junior and a senior, right? Because you're either a junior or a senior. These are disjoint events at both at the same time. They are mutually exclusive from each other because you cannot be both at the same time. So I'm drawing one thing, you can't draw both. Rule continued here. For two disjoint events, A and B, the probability that one or the other occurs is the sum of the probability of the two events. We've got some notation there that might be unfamiliar. Do you guys know what that means? A little U right there. What's that? You used to know? There was a time in my life when? No, it's not what it is. So this symbol means the union, okay? And what it kind of represents is or statements. So this is like saying the probability of event A or B. Essentially is what that symbol means. Its technical term is the union. We're probably never ever going to refer to it as that, but you know, just to throw it out there for you. When we see that symbol, we think or. That's the probability of event A or B. So the probability of event A or B is P of A plus P of B, and that is provided that A and B are disjoint. Okay. Finally, the multiplication rule. For two independent events, right? And we should probably make special note of that term right there. Independent events, A and B. The probability that both A and B can occur is the product of the probability of the two events. Right? Product. And then mathematically speaking, it's that. And again, we have this symbol right here. That one is the intersection. And in real speak, what do we say when we see the intersection? And. Well, you guessed well, right? So this statement right here is the probability of A and B. So that's the probability that both event A and event B will happen. Two independent events A and B are not disjoint, provided the two events have a probability greater than 0. And there's a nice picture of what independent, or the multiplication rule is. You've got two events. That overlapping portion is the portion that is A and B. This is the probability that both A and B will happen. And it's, where they overlap. A and B. You get the point. Many statisticians' methods require an independence assumption, but assuming independence doesn't make it true, we will look at some rules for when it doesn't make sense to assume independence. But we do have to think about we have to think about every step, right? We have to think about every step of the way, because independence is not necessarily something we can assume. All right, so we've got some examples here. We've got 4 minutes, which is not enough for us to do. So here's what I'm thinking we'll all do, because I want you guys to do some problems tonight. So what I think I'll do is during my planning period today, I will. I'm gonna go ahead and stop this video so that you don't have to watch it. We'll discard that.